we define a switchback. In the community, magnetic fluctuations, so these are Alfvénic structures, which means that there is a strong correlation between magnetic field and plasma velocity fluctuations. So whether or not there is a complete change in the polarity of the magnetic field, that remains to be discussed. But so in this particular study, what we did is that we looked for any rotation in the radial component of the magnetic field. Thanks to undergrads, we found many events from the first 8 encounters, of which we only identified the ones that have quality data available, and then ran it through a minimum variance analysis, which simply indicates the dimensionality of this structure, whether or not it's 2D or 3D, simply by looking at the eigenvalue ratio of minimum to the intermediate eigenvalues of greater than 2. We consider those to be 2-dimensional or higher. Therefore, of the 3,000 that we started with, only 1,400 candidate discontinuities survived, of which then we only looked at the ones that we have plasma data available. And the reason for that is that when we look at the type of discontinuity or magnetic discontinuity that switchbacks are, we're trying to look at, and what you see here on the x-axis is the relative magnitude of the normal component of the magnetic field and the relative magnitude of the normal velocity. These are ion velocity or proton velocity. So what you see here is that we break down, and the color bar here is the ratio of the number of rotational discontinuity to tangential discontinuity inside each bin. We ended up picking 0.4 as the region where we separate tangential discontinuity from rotational discontinuity, and that's simply an arbitrary value because that's what literature suggests, and that's what we stuck with. However, if you truly wanted, or if you want a true tangential discontinuity, these values simply should be 0. But that's not the case. Simply as long as they're small, we consider them a tangential discontinuity. So here's the overall distribution of the 500 switchback events. So bottom left is the tangential discontinuity, top right is the rotational discontinuity, and that's where the data points go. And in this case, the color bar is distance. So the first thing that you notice is that 46% of the events are rotational discontinuity type structures, and very few are tangential. Another 38% are in this region here that we actually haven't gone to look at exactly how to describe them. But when you look at the magnetic field and velocity conditions, these are actually incompressive type of structures because the magnetic field normal component jumps. However, the velocity doesn't change very much across the boundary. So it's interesting to see what type of behavior or how these switchbacks behave differently than those identified as tangential and rotational. And that's because simply there could be Kelvin-Helmholtz instability observed at those types of boundaries. So the other thing that we did with the 500 events is that we tried to look at the distance at which those switchbacks were observed versus the ratio of the number of rotational discontinuity to tangential discontinuity observed at that particular distance. So the bars here indicate the number of switchbacks in each distance bin of, I believe, 5 RS, that's solar radii. And then the data points here are the actual ratio of rotational to tangential discontinuity, and the color bar is the radial component of proton velocity. So when we look at this distribution, we notice that there is a exponential decay with the rotational to tangential discontinuity count as a function of distance. which suggested that as we move away from the sun, we wouldn't expect to really see any rotational discontinuity type switchbacks. And if you look at, if this continues to go toward the sun in the solar atmosphere, you would expect to see a lot of rotational discontinuity type switchbacks, indicating that potentially switchbacks, if generated in the solar atmosphere, there has to be a process that dominantly generates rotational discontinuities. And interchange connection is one of those possibilities. The other thing about this distribution is that this decay has a half-life of 11.6 RS. And the reason that's significant we'll come back to later. But the other thing to notice here is that the tangential or the exponential distribution, also we tried a different fit because we saw these outliers in the middle at around 35 RS. That fit a completely different distribution. We didn't really go into it in this study. We simply were focused on the type of discontinuities in this analysis, but we'll come back to that later too. But in this case, you see that the distribution is peaking at 35 RS, where the ratio of tangential to or rotational to tangential discontinuity maximizes. And the last part of that study was really looking at the magnetic pressure inside or magnetic energy inside of these switchbacks, and it's normalized relative to distance observed for both rotational and tangential type discontinuities. And what we found is that on average, magnetic pressure is 64% smaller in tangential discontinuity type switchbacks. And so one thing I forgot to mention here is that one of the things that this distribution may indicate is that switchbacks are generated as rotational discontinuity switchbacks and then evolve into tangential as they move away from the sun. Or that simply the two types of switchbacks are generated via different mechanisms. So this is at the time the type of mechanism that we propose for, and the idea of interchange connection being responsible for the generation of switchbacks has been around for a while. So we simply started with that and then formed these switchbacks as rotational discontinuities that simply stretched and bent and became tangential discontinuity and lost magnetic pressure throughout this process. And that's how we discussed, concluded switchbacks are pretty much relaxing upon generation. And through that process, if you remember the half-life of 11.6 RS, that means that if they're formed in the solar atmosphere due to interchange connection, within 11.6 RS, half of their energy is going into, half of that magnetic energy that is dissipating is going back into the plasma. And 11.6 is below the critical Alfvén point. So that's how we concluded that if that's the case, so much, nearly up to 16% of the reconnected energy is going again from the reconnection side into heating the plasma, not immediately next to the reconnection region, but almost 12 RS farther away from the actual reconnection site, simply because these bent field lines now have to relax and stretch. So that was the first study, and that's how we concluded that switchbacks heat the solar corona. But then as Parker Solar Probe got closer and closer to the sun, it dipped inside the below the critical Alfvén surface into the solar corona. And then what we set ourselves up for simply is to look for those rotations in the magnetic field to see whether or not we see these types of switchbacks as we define them in the solar corona. And that's exactly what we looked for. So we looked at the 14 Parker Solar Probe encounters, of which we found thousands of reversals in the magnetic field. Hundreds of them were switchbacks. And then we also found that Parker Solar Probe at least crossed the Alfvén surface 10 times. We had nearly 20 hours of data in what we call sub-Alfvénic solar corona. And then that's exactly where we started to look for switchbacks. Because based on our previous results, if switchbacks are truly generated in the solar corona, you would expect to see a lot of them in the solar corona. However, so here are the intervals where, and the duration in minutes of the sub-Alfvénic regions. And what we notice is that during these intervals, there are no BR reversals in the magnetic field, which completely baffled us. And then, so here is one example. As you can see, so here the magnetic field is shown in black, and cyan is the rotational, or is the radial component of the magnetic field. So you can see that as you get closer to the sun, you have these very strong fluctuations in the magnetic field and this is the line where it crosses zero. You have a lot of them crossing zero, but as you get very close to the sun, where magnetic field gets very strong. And when you look at the Alfvénic Mach number so the line here shows 1. The region where Alfvénic Mach number falls below 1 are the regions that we were interested in. And exactly at those regions, which I believe this is a zoomed in view, is that in none of those intervals, radial component of the magnetic field crosses zero. So there were two results. One, magnetic fluctuations, which we call pitch angles. So the fluctuation of the magnetic field not being larger than 90 degrees, because again, if it's larger, the polarity is changing, and that's how we look for switchbacks. So there are a lot of magnetic fluctuations, of which magnetic reversals completely disappear in the sub-Alfvénic solar wind. And that still may change now we're up to encounter 19. I haven't personally looked at the data to see whether or not this conclusion still holds. But if that's true, what that's saying about switchbacks is that they're either generated locally in the solar wind, so they're not generated in the solar atmosphere directly due to reconnection. So we call those in situ generation mechanisms, or that if, for example, reconnection or a process is causing the formation of these magnetic fluctuations, which are smaller than 90-degree pitch angle in the solar corona, those are finding the type of environment that they need in order to evolve into fully reverse switchbacks in the solar wind. So if there is an ex situ, so which means in the solar corona, if there is an ex situ process that is creating these switchbacks in the solar, generating these fluctuations in the solar corona, then they need to evolve into switchbacks as they propagate into the super-Alfvénic region. So they have to be generated in the eventually in the solar wind. So simply the takeaway message being that in situ mechanisms are necessary for switchback generation. And again, keep our definition of switchback in mind, that we require it to reverse polarity. So the picture that I showed you earlier, what we're finding out is that this picture is not as simple as we thought, at least based on our results thus far. What we think instead is that we still think that reconnection could actually play the role for generating these fluctuations that eventually turn into switchbacks. And the reason for that is that reconnection provides both the ex situ trigger mechanisms, so you have the breaking of the field lines, you have these other signatures, including the reconnection outflow that is pushing magnetic field and plasma out, also is generating these magnetic fluctuations that propagate along field lines that come into the solar wind. And it's really this process that triggers those fluctuations to form. And then as soon as you cross this surface, which is the Alfvén critical surface, and you come into the solar wind, is when those fluctuations then have the type of environment, especially the shear in proton velocity, that is cause them to go unstable and stretch into these switchbacks. So based on this picture, you no longer have switchbacks or reversal in the magnetic field in the solar corona. Instead, you have these fluctuations which turn into reversals in the solar wind. And that's why we say that in situ mechanisms are necessary for turning fluctuations into actual switchbacks. And so this picture so far agrees with our results. And of course, as I mentioned, switchbacks are Alfvénic structures. So these could simply be Alfvén waves that are turning into switchbacks as they go. However, that is yet to be determined. And of course, the study that just came out of the team here is that these switchbacks then can evolve as they move away from the sun and contribute to the heating of solar wind. So in this case, if switchbacks are contributing to the heating of solar corona, as we had originally indicated, it would not be direct contribution. It would simply be the Alfvén waves, or the waves that are generated from reconnection. Those that are dissipated in the solar wind are the ones that are heating up the corona, and those that, or which could be reflected or simply dissipate over time. But those that make it to the solar wind are the ones that can actually turn into switchbacks, which then evolve over time and can further heat the solar wind. So bottom line is that switchbacks definitely heat the solar corona, and likely indirectly can heat the solar wind, but also indirectly can heat the solar corona through those waves that reconnection could generate. So that was the first set of studies. How much time do I have?
Just a minute or two.
Oh, okay, perfect. So bottom line, the other study that we try to again look for the evolution of switchbacks is sometimes instead of just looking at instead of just seeing individual switchbacks, sometimes you see a bunch of them all together. That's what we call switchback patches. And then we look at other structures farther away from the sun that are called microstreams. Again, those are also flux tubes where it's very similar to a switchback patch, except it has a smaller number of switchbacks. And the overall background velocity, proton velocity, is larger than the ambient solar wind. So what we try to do is to look for a conjunction between Parker Solar Probe and Solar Orbiter, where they were radially aligned, and looked for an interval where the two observed switchback patches and microstreams. In the case of Solar Orbiter, it did not observe any switchback patches. There were very few microstreams in Parker Solar Probe data. I can't really go into the details, so I apologize. But some of the observations here that we found was, most importantly, when you compare the switchback patch observed at Parker Solar Probe versus microstreams observed at Solar Orbiter, you notice that dynamic pressure and thermal pressure jump quite significantly at the boundary of switchback patches. However, when it comes to microstreams, those nearly disappear, which indicates that the plasma inside switchbacks inside switchback patches may be equilibrating as they evolve, as they move away from the sun and relax. So this is the picture that these results, just trust me at this point, that these results indicate is that as we have these switchback patches, which is again a bundle of switchbacks, they simply de-stretch and relax magnetically and lose some of that kink in the magnetic field, and therefore it's switchback patches that are becoming microstreams. And again, through the process, they're losing their magnetic energy and also heating, but also accelerating the plasma inside microstreams. So the fact that microstream has a higher overall velocity than the ambient solar wind has to do with the relaxation of switchbacks inside those flux tubes as they move away from the sun. So that's what the color code is here trying to indicate. But yeah, so that's really all I have to show you. Bottom line is that switchbacks have shown us so much to indicate that they definitely contribute to not only accelerating plasma, but definitely heating the solar wind as well. And that is all. Thank you very much.
I think we have time for one quick question.
If nobody else does, I can ask some questions all day. Can you go back to the conclusions from part 2?
Part 2.
I want to suggest, no. Exclusively from part 2. So one more. There you go. Okay. So I would object to these being the only possible explanations. And I would offer another one, which
Please.
I think is Vamshi Yagarlamundi's assertion,
Yes.
which is that we've only crossed the Alfvén point a handful of times. I don't know how many times we've crossed it now, tens of times probably, but at the time of this, certainly only a handful of times, right?
Correct.
And those are very particular places, because those are places where the Alfvén surface had a finger that reached out to Parker's solar probe. It wasn't a place where we crossed. So we're not sampling the same sample of plasma. It's a sampling effect, right? We have an entire orbit where we're measuring lots and lots of switchbacks and everything like that. And then we cross the Alfvén point and we get one little window.
Yes.
And we're really studying whatever that particular little window was.
Absolutely.
It's not as representative of the rest.
Yes. So I 100% agree with that. And so for us, 20 hours of data was somewhat sufficient to draw a conclusion like that. But again, further encounters definitely could show intervals where there are switchbacks. And by switchbacks, rotation of the magnetic field in this sub-Alfvénic flow.
Right, but I mean, but his paper would say even beyond that, like he thinks all the places where we crossed the Alfvén point were actually trailing behind coronal mass ejections and transients. Right?
You're saying we never crossed.
I think it's an interesting argument that we've actually never, or maybe not until very recently, much more recently than this work, seen the precedent, the preceding plasma before the periods that you were studying.
I see. Understood.
We'll have to take this offline.
Okay, perfect. Thank you.
Let's thank our speaker again. Thank you, and it's my pleasure to introduce our second speaker, Casey Brinkman. She did her undergraduate at University of Vermont, or Vermont University? University of Vermont. And she recently graduated from the University of Hawaii. She's on the job market now, so if you run across her application, you should hire her. And today she's going to talk about compositions of rocky planets and the stars that host them.
Awesome. Yep, should be all set. Oh, I don't have speaker notes. One moment. I can just do it live, but is that okay? Is that right? Oh, okay, we're not going to do that. Okay.
Oh, you're mirrored?
Yep, that's okay. All right, well, can everybody hear me? Is this on? I don't think it's on. Hello? Okay. Just make sure. Oh, okay. Okay, hi everybody. Now it's on. Thank you for that introduction, Jason. My name's Casey. I just graduated from University of Hawaii, Manoa, working with Dan Huber and Lauren Weiss. And I have something in common with the entire field of exoplanets, which is that we were both born in 1995 with the discovery of 51 Peg. which means we're both rapidly approaching our 30th birthdays and getting a few gray hairs. But I have another really big thing in common with the entire field of exoplanets, which is I spent an embarrassing portion of those 30 years wondering about the uniqueness of the Earth in our galaxy, if it's unique in the cosmos and hosting life, or if it's a pretty average run-of-the-mill rocky planet. And so if we're assessing these exoplanets for potential Earth-likeness or potential habitability, one of the most important properties to characterize is its composition. So planets can, with a really broad brush, be thought to be composed of four main components: an iron core, a rocky mantle, some type of water layer or ocean, and a gaseous envelope primarily made of hydrogen or helium. However, for planets on short and ultra-short period orbits that are small, less than 1.5 times the radius of the Earth, they are likely too small and too hot to be composed of a hydrogen-helium envelope, and also probably too hot to be composed of a significant water layer. So for planets less than 1.5 times the radius of the Earth that are on short and ultra-short period orbits, we can assume that they are composed of just iron and rocky mantle. And we can estimate that ratio of iron core to rocky mantle using mass and radius measurements for these planets. So this is the curve in terms of planet mass for a planet with an Earth-like composition of roughly 30% iron, 70% rock. This is where a planet would fall if it is just iron and has no significant rocky mantle. And any measurements that fall below this on a mass radius diagram would have to be more dense than iron and are probably just a measurement error. If a planet contains no iron core and it's only rocky mantle, it'll fall up here, and any planets falling above this on a mass radius diagram are likely hosting some type of a gaseous envelope or low density component. So that means planets that we expect to be composed just of iron and rock would fall in this region of parameter space and would be a rocky planet. So if we want to see the diversity of compositions for rocky planets, we plot planets that have masses characterized to 30% uncertainty or better from NASA Exoplanet Archive, and see that planets not only span this full range of expected rocky compositions, but that some appear to be 100% iron or even more dense, and that some appear to have gaseous envelopes similar to a sub-Neptune, even though they're smaller than 1.5 Earth radii. So to investigate whether or not this diversity of compositions is real or simply a figment of poor uncertainties on these measurements, we targeted 7 planets and for extreme precision RV follow-up using KPF and Gemini Marin X. So we spent 3 years of my dissertation collecting data from these telescopes, collected hundreds of RVs on these 7 planets, and in particular, we focused on high cadence observations, so collecting as many RVs per night as possible. This is to mitigate 2 things. One is stellar variability and uncertainties, and then the second is these are both very new spectrographs and are prone to instability from night to night. And in addition to characterizing the masses of these rocky planets, we wanted to do a homogeneous characterization of their host stars. So using spectroscopic values for effective temperature and log G, et cetera, we used isochrones to update the stellar masses and radii, which allows us to use literature values for RP over our star in order to update the planet masses as well, or planet radii as well. And the first planet in our study is a planet that's very special to me, TY 561b. This is a unique planet for many reasons. It's one of the only Earth-sized planets that orbits around a thick disk star. As such, it's one of the oldest Earth-sized planets that we know of at roughly 2/3 age of the universe. And it's also an extremely hot planet, has half-a-day orbit, meaning its equilibrium temperature is roughly 2,500 Kelvin. As a thick disk star, TY 561 is one of the most iron-poor exoplanet hosts that we know of at -0.4 dex. And it's also enriched in alpha process abundances, such as magnesium, silicon, and oxygen, which are all rock-building species. So as such, we would potentially expect this planet to have a smaller iron core relative to its rocky mantle than the Earth. But because it's so small and so hot, we would potentially not expect it to have a gaseous envelope. And these are not what we see with the literature masses and radii when we started our survey. One of the mass measurements in the literature measured using high-res suggests a iron-poor rocky composition. similar to what we would expect, while the other, measured using HARPS North, suggests a substantial gaseous envelope. So to break this degeneracy, we wanted to use a third independent spectrograph. So we targeted this with high cadence RVs from Maroon X and measure a mass and radius that place it right on the boundary of being a rocky planet or needing a gaseous envelope. The best fit mass and radius place it, say it should have a gaseous envelope, but 1 sigma uncertainties put it within that rocky planet regime. So to break this degeneracy, we're eagerly awaiting a phase curve from James Webb. PI Joanna Teskey just got this data from NIRSpec a little while ago. And this will help us determine if there is heat redistribution from the presence of a gaseous envelope or if it's in fact bare rock. And we published our analysis of this planet last year, if you are curious and want to learn more about TY 561b. But I only have 15 minutes, so time to tell you about a different planet. So Kepler-10 was the next in our survey. It's also orbits around a thick disk host, and as such is fairly iron poor and alpha enhanced, but not as severely as TY 561. So we targeted Kepler-10, which is already a pretty well characterized planet, with KPF and Maroon X, and found, unsurprisingly, a mass that is in agreement with previous measurements and moved ever so slightly closer to that Earth-like composition line. And then the next one is Kepler-407b, which is a planet that had a lot of RVs, but a shockingly large uncertainty on its mass measurement, and suggests a relatively iron-poor composition as well. But again, those 1 sigma uncertainties are huge. So we targeted it with really high cadence RVs from Maroon X and KPF, and have measured a more precise mass for the planet that, again, shifts it towards this Earth-like composition line. Next up, we targeted 1444b, and with a bunch of RVs from KPF, it was fairly consistent with previous measurements and very consistent with an Earth-like composition. And that does it for the lower density planets. Next, we looked at several of these quote-unquote super-Mercuries. And one of the most famous of which is Kepler-100b. Mass and radius measurements for this planet said that it was nearly 100% iron when we began this survey. And after targeting it with Maroon X for a couple years, we found that it still seems to be a little bit iron enhanced with a core mass fraction of roughly 60% iron, but much less severe than previous measurements suggested. And then in a similar region of parameter space, we looked at HD 93963a, B, that's a mouthful, and both with high cadence observations from KPF and a new value for RP over R star, which is kind of tricky because it's a binary system. So with the correct treatment of binarity and dilution, we see that it falls exactly on that Earth-like composition line, and its 1 sigma uncertainties don't even say it could be a super-Mercury. So in addition to these planets that we carefully selected to test the diversity of compositions, we had the opportunity to confirm another Earth-like planet, TOI 1011b, so with new precise mass measurement with Maroon X and HARPS North, and with a nice radius measurement from TESS, we find that, surprise, surprise, it has an Earth-like composition. And so these updated masses and radii are really helpful, and these extreme precision RVs have been really critical in our recharacterization of these planets. But getting newer and better RVs aren't the only way of updating a mass measurement for a rocky planet. And so we then looked to Kepler-102d, which orbits a particularly active star. So stellar activity can cause suppression of convection due to the magnetic fields in the star, and this can actually impact the radial velocities that you measure. And as the star rotates, this can sort of mimic the signal of a transiting planet, and it can really interfere with your measurement of an RV semi-amplitude. Luckily, this signal can be easily fit using a Gaussian process. And so we use a Gaussian process that we actually train on the photometry from Kepler, because Kepler photometry is far better sampled than RVs could ever hope to be. And we're able to constrain the hyperparameters of a quasi-periodic Gaussian process model that we can then apply to the RVs and measure a much more precise mass, or not precise, actually, it's a much more accurate measurement for this planet mass. And shocker, it moves from this super-Mercury regime down to a more Earth-like planet, even though it still has very large mass uncertainties. So I'm sure you've kind of picked up on the main point of my paper by now, which is that after recharacterization, the compositions of every single planet that we looked at became more similar to that of the Earth than they were before, the exception of TOI 561b, depending on which prior literature value you adopt. To quantify this a little bit, we looked at the fractional root mean square uncertainty before and after recharacterization and find that this gets cut in half, meaning that it's an Earth-like composition would be a better fit to our data after, even though we're not quantifying it in that way exactly. It appears that the diversity of Earth-like compositions is less so than previously thought, and in particular, the largest change comes in from this adoption of these super-Mercuries into more Earth-like regime. This is in harmony with a lot of other mass recharacterization papers from others, as well as from theory that shows that it's really challenging to form Earth-sized planets, or planets that are larger than the Earth that are enriched greater than 50% in iron, and that we don't actually expect to see many of these planets out in the wild. But the compositions of these planets did not fall out of a coconut tree, and they exist in the context of all that is and came before them, and we can compare the compositions of these planets to that of their host stars. So here on the y-axis, we show the composition of planets, this core mass fraction. So 0 is no iron core, 1 is it's all iron, and a negative core mass fraction just indicates that this planet likely has some type of a gaseous envelope or low density component. And then on the x-axis, it's this stellar equivalent core mass fraction is what you would expect the planet to be if it inherited the same ratio of iron and magnesium and other rock building abundances as its host star. And this this dotted line is the 1-to-1 line. So this is where each planet would fall if it indeed has the same composition as measured from its host star's spectroscopic abundances. And this is where, and then Venus, Earth, and Venus, Earth, and Mars are in the middle there, and Mercury's way up top to just show the spread of compositions in our own solar system. And this is where the planets that I've just told you about fall. So these 4 in the middle are all in agreement with their composition of their host star to within 1 standard deviation. Kepler 100b is still up there at the top, showing up as a little iron enhanced, while TOI 561b appears to have a negative core mass fraction or some type of a gaseous envelope. In a paper that I recently released on arXiv last week, we can also compare this to a larger sample of homogeneously characterized planets and host stars, where we see that 75% of these planets have the same composition as their host star to within 1 standard deviation, and 25% are either greater or lower. And what do we want to do with a bunch of scattered data but fit a line through it, obviously? So in order to try to replicate previous studies on this, we wanted to do a linear fit. But to try to do so in the most physically meaningful way possible, we use ordinary least squares, and we use a process called rejection sampling. So this means that in order to estimate the uncertainties and to only use physically meaningful values of core mass fraction, we draw 1,000 points for each planet on this in terms of, from a Gaussian distribution centered on these values in terms of the core mass fraction of the star and planet. And every time we get a planet value that has a negative core mass fraction, we throw that planet out of the fit, because in that trial, it's not a rocky planet if it's not consistent with a positive core mass fraction. And the result of this is this purple line that you see here has a slope of 1.3, so it's very similar to this 1-to-1 line between star and planet compositions, but still has fairly sizable fractional uncertainties. So it's not a super statistically significant fit. This is in really stark contrast, though, to previous fits from Wu and Ni 2023 and Adebekian et al. 2021 that suggest an extremely steep and statistically significant relationship between star and planet compositions. So this paper is coming soon. I'm going to be submitting it this Friday and posting it on arXiv, so check this out next week if this has been of interest to you. And to quickly summarize, we looked into the diversity of Earth-sized planet compositions and found that in many ways it's not as diverse as previously thought, that planets tend to be Earth-like, and they're in particular far fewer super-Mercuries than previously thought. And in other ways, it's more diverse than we previously thought, because not all planets with 1.5 Earth radii are in fact rocky, as shown by the likelihood that TOI 561b probably has a gaseous envelope. And with that, I'm out of time, and I'm happy to take any questions.
All right, thank you. Questions?
Thanks, Jason. Okay, so thank you. It's really comforting to see that those supermercuries
Yeah.
don't seem to be real.
Yeah.
One of the most simple, profound predictions of the core mass theory is that the core mass, the iron fraction of a terrestrial planet should match the stellar abundance, especially for things that are relatively massive. So,
Yeah.
so you largely got new data, and with the new data, you got these much more reasonable iron mass fractions. Did you try figuring out what the other, was it that the other groups did their analysis wrong in the sense that they made a math error, or they didn't account for stellar variability in a sophisticated way? Or did you try reanalyzing their data, and did you find that actually you got the same estimate, and for some reason there are just much larger outliers than one expected between the two results? So what's the origin of this initial finding of many planets where they were massive, in your opinion? Any
Yeah.
candid thoughts would be really
Yeah.
appreciated.
No, it's a great question, and it's really planet dependent because each planet and its host star are so different. For most of the systems, I think, so I did always take the previous archival data and fit it and made sure I recovered what previous publications had gotten. So it's not like an error in the, Keplerian orbital solutions. Those are pretty simple for the fits, and I don't think anybody was wrong before, but the data in particular was had large uncertainties if it was from something like high res, and also low cadence, which is huge because so many of these systems where you get 1-2 RVs a night and then you stack them together, there's so much scatter. Even for stars that are fairly quiet, fairly old, and wouldn't benefit from like a quasi-periodic GP or anything. But when you get a ton of RVs a night and you can pretty much sample the full orbit, it was just coming out a lot smaller and a lot tighter. So I think in large part it's the precision of the RVs and the sampling rate.
Great.
So 2 questions. Thanks for this very nice and illuminating talk. With regards to what you just said, though, does that mean that people in general who are claiming supermercuries were underestimating their error bars throughout the process?
Potentially. I think I think people were reporting the semi-amplitude and uncertainty that you get using an MCMC on that from like a simple fitting code such as radval. But I think that there was sources of scatter beyond what they are accounting for in the radial velocities.
Right, okay. All right, thank you.
Yeah.
And then the question about this gassy small planet. Can you remind me what you know about the star? What's its spectral type and the distance to the planet?
Yeah, so it's a G-type star, but it's a thick disk star. So it's really old, really quiet, very iron poor. And the planet orbits it at orbit of half a day. So it has a really high equilibrium temperature of like 2,500 Kelvin. So you definitely aren't expecting a hydrogen-helium envelope. That would dissipate very quickly. From some back-of-the-envelope calculations that I did, water is a potential, CO2 is a potential. It could also be evaporated silicate mantle, which is kind of like a really exotic composition that you would get, which would primarily be a sulfur-based atmosphere if it's actually so hot that it's evaporating the rocky mantle itself. We probably can distinguish between that and CO2 or H2O with a phase curve, but we'll see how good the near-spec data is and if we want to get MIRI data or something like that.
One more quick question about your measurements. The final values that you quoted, is that just from your data, or did you combine all of the data that was previously published?
For the most part, I used the publicly available data in combination with it. The only planet where I didn't use the high-res data was HD 939638 because it was just really all over the place, kind of.
And did you try just fitting yours independently?
Yeah, so the value that I report is, I think, is just using the KPF, the high cadence KPF data, because it hurt the fit to use the old data. So in that case I didn't, but for the rest I think I did.
Great. Any other questions?
Okay, so in your opinion, are there any surviving supermercuries where you agree that the density really is not consistent with the stellar ratio of iron to magnesium silicates?
Well, the only one in my sample that I've looked at that I think has a chance is Kepler 100b. I have the RV fits down in here somewhere.
But even outside of the sample?
Yes, outside of the sample of that I've looked at, I think, no. I think that, because
That's right, that's a profound.
no, and I think that as we get able to look at smaller and smaller planets, we might start to find some. You know, if we get to measuring sub-Earths, okay, now you're starting to think things that could be Mercury-like, but above the Earth, probably not. This one, maybe, but we'll see.
All right, great. Let's thank our speaker again. And there's still room in her schedule at the end of the day if anybody wants to meet with her. Thank you.